automatically be like, oh, do first difference. If first difference is the same, it means it's linear, right? But to understand, oh, because the x's are the same intervals, if I go up 2 each time, I am making a straight line, right? That's what this first difference tells us. So let's take the first difference of the first graph. Now, we can only do the first difference if the x's are going up by the same amount, right? So what do we do? Bottom minus top or top minus bottom? Bottom minus top. Good. So if you forgot what first differences is, it's going 2 minus 0 equals 2, where difference is the first time you take the difference of the y's. So we're looking at how is this function changing. 4 minus 2, right, is 2. 6 minus 4. Folks, what does this 2 represent? If I were to graph this function, what does this 2 represent? It does. So the first difference is the slope of a linear function. Anyone remember another word we used for slope in grade 9? Rate of change. Rate of change. How fast or how does it change? Well, it goes up by 2 each time you go across by 1. That's a rate of change, and that's what slope means. What if I instead made a mistake and said, oh, no, you go top minus bottom, 0 minus 2. Would that be okay if I just did it each time? Why not, Luke? That's right. And show me with your arm, what would a line with a negative 2 slope look like? Oh, right. So it would be the opposite slope. Okay. So in math, we're always going left to right. So as x is growing, how is y changing? It goes 2 up each time. All right. So, so we can say this is a linear function because what? Pardon? Like the first differences are constant. So linear functions have first differences that are constant. Constant meaning they don't change. And second difference is equal to what? Oh, let's see. So the second difference is when you take the first difference and subtract them. So meaning 2 minus 2, what's that? What's 2 minus 2? 0. Okay. Next year, when you take advanced functions and calculus, you're going to learn about derivatives. And derivatives are basically a second difference. Okay. So what we're saying is the slope doesn't change for a linear function. How about a quadratic function? If you are able to find the slope at different points, does the slope change? Yes. Like that's a bit tricky. But imagine I've got a parabola. And imagine that somehow I'm able to find the slope at all these points. Like the minute slope. Is the slope changing at these points? Right? Like here, it's like this. Here, it's like this. Here, it's like this. Right? That's we basically draw a tangent to find the slope at each of those points. And so for a quadratic function, the slope is definitely changing. Right? And that's part of the first difference. So let's do this one that you all said, oh, it's x squared. Why? Well, cause. So again, are the x's going up by 1 each time? Good. So I can do this. All right, so let's do the first difference. 1 minus 0, 1, 4 minus 1, 3, 9 minus 4, 5. Before you do the second difference, what do you notice about the first difference? What is it, Greg? It's the step pattern. Do you see that? 1, 3, 5. What would the next number be? 1, 3, 5, 7. So what's the next At 4, what does y equal? 16. It's the step pattern. Let's make a note. First difference is saying when I go across one, how much am I going up? Well, isn't that the step pattern? Go across one, go up one. One across 3 up, one across 5 up. All right, well, let's take the second difference because that's just the cool thing to do. And we all want to be really cool mathematicians. Okay, 3 minus 1, 2. 5 minus 3, 2. What if I did 7 minus 5? Okay, so what can we say about the second difference? Constant. Good. So let's write that down. Quadratic functions have first differences that are, let's just say, not constant. Right? So they're not the same number, but we definitely see there's a pattern. And then when we take the second difference, or what you will call the derivative later on, you'll be like, oh, there is a constant second difference. And the second differences that are constant. So will the second difference always be 2 for a parabola?
No. Actually, yeah. No.
Like, don't just say no. Like, I don't know. Will it? What are you thinking, Luke? Can you see his brain? It's actually like the wheels are turning. Okay? C value or vertical stretch? Which one?
I don't know.
No, it's a really good thought. So Luke is going into the transformations. So think about this. Talk with your partner. Will the second difference always be 2? And as what should I think about? Think about AKDC. Go. All right, pause. Is it AKDC? It's A, right? And I heard Clara say it so well. It's the vertical stretch, right? So the step pattern, how does the step pattern change? Well, we multiply it by 8. So if A is, good morning. Did you sign in?
No.
You got to do that. You got to go to the office. So if the A value is 1, the second difference will always be 2. Well, what if the A value is 2? What will the second difference always be? Right? Good. Okay. So we're really analyzing this. I love it. All right. Let's move on to this third one that you're all like, oh, it's going to be, what did you say? 2 to the x. Okay, great. Good for you. How did we get that? First of all, what did we notice about the x's? Good. Thank goodness. I want to add one more. What's the next y going to be? 16. And what are we noticing about the y values? They are doubling, right? So as soon as we say doubling, we're like, oh, that's what we talked about yesterday in class, the doubling effect, right? So it must be exponential, right? The pennies yesterday, every day the amount of pennies doubled, that's exponential. If it halves, it's also exponential. But how do we show that with our analysis? So what's the first thing we're going to do? Yeah, that's a great idea. So first, difference. And include the 16 in your calculations. We just need a few more numbers. 2 minus 1 is 1. 4 minus 2 is 3. Am I doing this right? No. 8 minus 4 is 4. 16 minus 8 is 8. Okay. So what can we say? Not constant, right? All right. So what do we do now? You are right. Let's do the second difference. Thank you. You can recycle that actually. Just so it's if you're more than 20 minutes late, you have to go to the office. Okay, 2 minus 1 is 1. 4 minus 2 is 2. 8 minus 4 is 4. Anyone notice something interesting? Okay. Is it constant? What do we do? Third difference? I mean, let's see. What happens when we do a third difference? Any thoughts? 2 minus 1 is 1. 4 minus 2 is 2. What's going to happen then? If I had another one, if I had 32, I had 16, I had 8, I had 4. So what's going to happen? It's going to be the same. And if I take a fourth difference, it's going to be the same. Okay. So we can just say not constant. But I heard someone say it. What do you notice about the numbers? They're doubling. They're still doubling, right? So we actually don't traditionally do a third difference, but I just wanted to explore that. Will it ever be constant? No. So first of all, which function is this? It is exponential. It's growing exponentially because it's doubling. And what we see is there is no first, second, third, fourth difference that will produce a constant value. But what we do have is a constant factor. This is increasing by a factor of 2, like it's doubling. Okay? So first of all, we need to label these functions. We said this one is linear. This one is quadratic. And this one is exponential. And so this is, now that we really looked at it, do you see how beautifully we analyzed it? So in an exponential function, first and second differences that are not constant. However, there is a constant factor between them. Because there are more functions to look at, folks. There's a gazillion functions, but this is how we can recognize an exponential function. So what you will do is you will do exactly what we just did for question 1, right? So not now, but you're going to add question 1 to your homework so that you can practice what we did. All right? Sure. Let's move on to today's lesson. Isn't this exciting? So that's a good question. We said that the first difference gives you the slope of a line, right? But what if the x's are going up by 2? Is it giving you the slope? No, it's giving you it's a bit of a skewed number, but it will still give you a constant value. I don't actually know the answer, Luke. I like that question, and I think it's worth exploring. Okay? All right, folks, give me a beautiful exponential function with exponential growth. Right? So if I'm mirroring you, Greg, are you growing? Pardon? Are you injured?
Yeah.
Oh, I'm sorry. Okay, don't injure yourself more. It's a math injury. Woohoo! First, all right. Exponential growth, exponential decay. And here's the question. This is what Kajik did. Wait. Sorry, Kajik. I'm sorry but it's such a good mistake. Kajik did this. Okay, maybe I'm kind of what's the mistake?
It breaks 0.
Beautiful. Don't forget that you're going to have an asymptote. Oh, that was so good. the math high five. There's an asymptote, right? So don't forget. All right, now go back to your exponential growth. Okay. What if I change the A value? I give a higher A value. Beautiful. Does your asymptote change? No, but it gets steeper. Is it growing faster or slower? Good. All right. Actually, get up, folks. How can I not? Is it necessary? Yeah, it's kind of like you can't not. Whoa, I don't like that. No, it's not good. Like, what are all these fake outs? Yes, that's what I meant. All right. Oh my God, you're analyzing the aerobics? Oh, exponential? Oh my God, you're so good. Just so we're not distracted, I won't show you the video. Okay, good job. All right, I'm glad that had a lasting effect. Okay, so we got our exponential growth, right? Now, if I increase the A value, what does it look like? Good, steeper. Asymptote changes? No. Okay. Go back to a regular exponential growth. Change, we're going to have a negative C value. Beautiful. Negative C value. Did the asymptote change? It did. Let's get a positive C value, like +5. That's right. Thank you, Marley and Liam. What if I have a positive C value? Dudes, folks. Right? Oh, Kajik is on his tippy toes. That's so cute. Did your asymptote change? Beautiful. Go back to an asymptote of 0. C equals 0. Okay. What if there is a D value of 5? What are we doing? Right? You're going, okay. I just ignore me because I'm backwards. Did you change the asymptote? Good. What if it's a D value of -5? Thank you for doing the grapevine. Did the asymptote change? No. All right. Here's a tricky one. K, listen up. K equals -1. K equals -1. Did I heard her say A to the right? No, she probably said 8, but I said 8. Right? So, folks, if I do this, talk to me. What is this called? Yes, but now that we know that this is exponential growth, interesting. All right, go back to, okay, we're in exponential decay. Give me a negative A value. Negative A value. Nope. Okay, Greg is really trying. No. Yeah. There you go, Greg. It's a negative A value. No, there's a monkey bar. What's the monkey bar? The x-axis. Thank you, Marley. The x-axis is the monkey bar. It's like this, folks. Right? Yeah. Did I change the asymptote? But tell me, will the range be different? Because now we're less than 0. Beautiful. All right, that was a great warm-up. I'm so sorry. But Marley, I will tell you, like, parabola or functions aerobics gets better each year. So you definitely have had more of it than the class last year. Okay, so like, I'm getting really excited. Yeah. Like yeah. Next year, I want to do it in the gym, like on the actual aerobic blocks.
Functions aerobics.
Oh, that would be amazing.
I would join too.
Or like if I could go to a gym class and do like be like, yeah, like PFit. I'm gonna do. Yes, I like it. That's like cross curricular. Yes. All right. Okay. So folks, the great thing about this unit is the only new thing is this new type of function. We still have a k, we have an a, d, c. Great. Okay, we just have to learn this new function. All right, so let's review what we know. A is a vertical stretch by a factor of a, right? Nothing new. What do we do with the a? We multiply the y values by a, right? So it's a times y. If a is greater than 0, then there is, if a is less than 0, then there is what?
Reflection.
Done. We know that, right? This is like a review from last unit's test. Beautiful, which I haven't even touched. I apologize. All right, next, k. Okay, horizontal stretch by a factor of 1 over k, right? We always know we have to do the 1 over k. Multiply all x values by 1 over k. And if k is less than 0, there is a what? In the y-axis, right? So now the y-axis is the monkey bar. And so if I do mapping notation, I'm basically saying x divided by k. Someone actually picked up this booklet, flipped to the 3rd page, and they're like, oh, I must have gotten the wrong booklet. This is exactly the same, right? Yeah, doesn't it feel good to be like, I know what you're talking about, Miss Sly? Good. D, horizontal translations, d units to the right. Recall, if you see x plus d, then d was originally negative, meaning a shift to the what? Left. Right? So if it's x plus 5, we're going 5 to the left. Okay, so how do we map that? X plus d. And then we have C, which is the vertical translation, which changes the horizontal asymptote, as you guys figured out. Okay, if C is less than 0, the vertical translations is C unit what? If it's less than 0, meaning it's negative, then we're going down. Right? C is the nice one. That is just Y plus C, whatever C is. And let's recall mapping notation. Let's just write it down. So it's going to be x over k plus d, right? So you're going to first apply the stretch and reflection, the RS, and then the t at the end. And then for the y, we've got a times y plus c. Just as a little review. Now, in chapter 4, we had to learn the parent functions, and we have to do the same for the exponential function. We need to know the key points for the exponential function, okay, of the parent function. So, oh, shoot, I forgot these questions. No, we can skip that. All right, so generally what we're going to do is we're going to pick 4 points or features on the original parent function. Now, this is where it gets tricky. If we have a function that is doubling or tripling or being multiplied by 10, the key points are going to change. So the way that we choose our key points is like this. Key points, where the b is the base of the exponential. So if I have, for example, if I have y equals 2 to the power of x, that means my b equals 2. Okay, so I'm going to show you how we find these key points in the next question. But that's just 3 key points. So the other feature is the asymptote, right? And what is the asymptote of all original exponential functions? Y equals 0. That doesn't change. As your b changes, the original asymptote does not change. So let's put this into play. So what we're going to do today is we're going to figure out the transformations, and then we're going to sketch them. We're going to sketch the function. Given the function f of x equals 2 to the power of x. So if is this growth or decay? Great. Describe the transformations involved, provide a rough sketch, and state the domain and range. So once again, we're getting function notation. So all we're getting is this. So as a review, let's write down AKDC. All right, so what's your A? What's your K? What's your D? Okay, so I know that A is the number at the front. So that's my 5. I know that number at the end is my C. There is no horizontal movement, and there's no stretch. So K is 1. So we really only have 2 transformations here. We first list the RS, the reflection and stretch. So the first thing we've got is a vertical stretch by 5. And then the C tells us we're moving up by 4, right? So we can say vert, translation, trans, 4, up. And so just quickly, make your regular parent function, apply a vertical stretch of 5, and vertical translation of 4, we're moving up. Okay, so you're like, oh, I know what I'm looking for as a final function. Now, I want to go back to those key points. Okay, so we're going to figure out the transformations using mapping notation. So let's first make a table of values of the original parent function. Well, what points do I use? Well, I go back to this box. In this case, what is my b value? 2, right? The b is the base of the function, the base here under the exponent. So if it's 2, that means my first point is x is negative 1, y is 1 over 2. So I'm taking my 2 and I'm plugging it into this orange box. The next point is 0, 1. Right? Remember we saw yesterday that the y-intercept is always 1 unless we're going to have a stretch or a vertical translation. And then the next point is 1b. So if x is 1, y is going to be b, which is 2 in this case. Now, we're not going to graph the original function. We've already done that in our head. What we're going to do is figure out the mapping notation to find the transformed function. So, yeah. So our transformed function has the mapping notation of 5 f of x plus 4. let's have you practice writing the mapping notation. So what is the x going to look like? Well, that's not changing. How do we find the y? Right, it's going to be 5 times y plus 4. Now, as we find the transformed points, I'm going to just use decimals. So the great thing is the x doesn't change. So x stays as -1. Okay, if y is 1/2, if you need your calculator, fine, but try to do it in your head. 5 times 1/2 plus 4, so it's 2.5 plus 4, 6.5. Again, x doesn't change. And we also must consider the asymptote. So it starts off at y equals 0, and it ends up at y equals c, right? Y equals c, which is what? Y equals to 4. So now, how do I draw this? Now, I think one of the things is people are unclear how to draw asymptotes on the graph. It has to be a dotted line. You have to actually draw the asymptote. So watch. Here's the asymptote. Dot, wait. Dot, 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 dot. And then you must label the asymptote as y equals to 4. Okay, this is how you draw and label the asymptote. Sorry, I didn't realize you can't see. Please tell me. Can everyone see the board? Okay, so now that I've got, now this is a sketch, right? So it might not be fully accurate. Okay, and now we draw our points. So keeping in mind, we have to get to kind of 14. So this is going to be 4, 8, 12, 16. I don't know, I'm kind of estimating. So at 1, it's going to be about there. At 0, it's going to be about 9. Right? I was like, okay, this is. Right, I really estimated. This is 16. This is 12. This dot is 8 because this is 4 and that's 0. You don't even have to put numbers down. It's just kind of, it might be helpful. And at -1, it's going to be 6.5. And I know that the function is approaching the asymptote. So I can see, oh yeah, we thought it was going to shift up. Are you okay there? Okay.
Where did we get 16?
We didn't. The 16, no, this is 14.
Wow.
This is 114, right? I just drew the 16 to sort of have a scale on the graph. So does it increase faster? Yeah, it does. Did it shift up as we predicted? Yes, it does. Okay, and then folks, another thing you need to do is you need to label the graph. So we can label it with the function notation as given. 5 f of x plus 4. Hey, Miss Sly, this is a graph of this function. Okay? Let's try another one. Привіт, доброго дня.
Oh, we have to do domain range.
Oh, thank you. How did I forget that? All right. Okay, domain. What is it, folks? x belongs to real numbers, right? Unless I'm restricting my function on purpose, the exponential function is always has the same domain. And range is pretty simple. It just has to be bigger than what? It has to be bigger than the asymptote. So in this case, it's y is bigger than 4. Thank you, Marley. All right, let's do the next one. Now, as you look at this function, I know we are confused. What are we confused about? Look at it. Tell me what you're confused about. What is it, Greg? Say it again. The x isn't what? The x isn't isolated. Coefficient. What else is confusing here?
There's a reflection.
Anyone confused by the f? What does it tell you, Liam?
And it's a function.
Yeah, which one?
Well, we already told in the question.
Okay. Yes. So this is B. This is a continuation of example 1, where the function has to be defined, right? You can't just get function notation and be like, I know what to do. No, you need to know what the function is. So we were told earlier that f of x equals 2 to the power of x. So all these questions on this page are working with this doubling exponential function. All right, so let's just write, okay, what do we have here? We've got a equals -2. And what is the 3? It's my k value. All right, so let's write mapping notation. Actually, wait, pause. Key points. Do we know the key points already? Yeah, we do. Same ones as in the last question. So I had, was it 1 or -1? -1, 1/2. All right, I'm just copying from the other question, 0, 1, and 1, 2. And then I had the asymptote of y equals 0. And now to figure out the new transformed points, I'll write mapping notation specific to this question. You want to give it a try? So if you forget how to do mapping notation, look at our note here. We wrote x over k plus d, right? I'm going to write it down. You ask me questions if you're not sure. Sort of as you're doing this, why don't you check, are you on track? You don't have to put all these arrows down. We're doing a lot of work with fractions. If like I'm writing -1/3 because I hate rounding, but in my head I'm like, I know that's -0.333, right? And as I'm plotting these, I'm like, oh yeah, I can see it's getting horizontally squashed. Anything happen to the asymptote? No change. So first thing you draw the asymptote and label it. Get into the habit. Because I'm going to really come down. I'm going to be really strict about taking marks off if the asymptote is not properly drawn and labeled. So it must be a dotted line. And like, if you need to draw it right below so that it's visible, that's fine. right? You can like draw it right below, right above kind of thing. But the labeling is what gives it away. Like, oh, that's an asymptote of y equals 0. Yeah.
Why is the y along the x-axis?
Good question. So when we have a horizontal line, we look at what's never changing. The x values change all along the x line. But what is y at every single point here? 0. So that's how we give that equation. Now, folks, sorry, we forgot to do our aerobics. So let's think of this. We start with f of x equals 2x, right? I'm mirroring you folks. Okay, apply -2. A equals -2. So first of all, we go upside down and steeper. Yeah, a faster. Yeah. Is this growth or decay now?
Decay.
It's decay. Yeah. And now k equals 3. Are we getting horizontally squashed or stretched? We are. So it's even steeper. Good. Good. Okay, so I kind of know what graph I'm expecting. Okay, at y equals negative, so I need to get, I'm just putting a scale here, right? Just so I kind of know what to do. Okay, when x equals -1/3, y equals -1. When x equals 0, y equals -2. When x equals 1/3, y equals 4. Now I know it's heading towards the asymptote, and because it had a vertical reflection, so we can call this decay. So this function went from being exponential growth to actually decaying, and that's because it's getting smaller and smaller. Or actually, so let's not say decay, let's say decrease. That is not decay. There's a different, yeah. All right, Claire, I lost half a mark. Why? That's right. Poor Miss Sly. She forgot to label the function. What was it? -5? -2. There we go. Beautiful, Miss Sly. Well done. Okay, I'm going to give you these next two for homework. Okay, so homework, HW. Next one, HW. If you're unsure of what to do for this, folks, you can take a page out of Greg's book and come to extra help and do your homework there. So that way, if you have questions, you get to ask Miss Sly right away, right? Does it work? All right. It's after school. Yeah. Yeah, there is. And it's after school. So it's like, hey, I'm just going to go after school, do my homework, get it done. Right? It's actually a pretty good way of doing it. Yeah. Sorry? Oh, domain and range. Thank you. Across the hall. And keep in mind, sometimes it takes me, Sebastian, like 5 or 10 minutes to get there if I'm like teaching another class or something. But I will be there. You can walk in and start doing your homework. Yes. At lunch. Yes. I'm back to a regular schedule. Robotics is over. Did domain change? No, it's still growing in both directions. So it's the entire x-axis. Did the range change? Well, the asymptote didn't change. But the domain is a bit tricky. Oh, sorry, the range is a bit tricky. What do I say? What goes between the y and the 0? Greater than or less than? Yeah. Now, y has to be less than 0 because it's under the asymptote. So that's what changed. You see that, Kajik? So it used to be above. Now it's below. So the one thing that changes is the less than sign. Great. Okay. So do the next two for homework. Does this feel good, folks? Like, are you kind of like, okay, I kind of know what I'm doing here, right? And do you remember how I told you chapter 5? I said midway through the year, you're going to feel like you're getting it. This is now, if you don't do your homework, you are not going to see the results. But if you do your homework, you will be like, things are going to click. You're going to feel much better. We've made it. All right. Example 2. State the transformations required to get the graph of this. Oh, sorry. Plus the 1. From the graph of here. So notice, you have to be told that the base is 3, right? So let's, first of all, remember to factor first if possible. So let's take this original function. Is it doubling, tripling, quadrupling? What's it doing? What type of exponential growth is it? It's tripling. The 3 tells me it's tripling. All right, and I have to factor the exponent. Now, this is a bit new, right? You're like, I don't know what I'm looking at, Miss Sly. Let me help you out. Let's do like a process of elimination. Does anyone know what the plus 1 is? Yeah, this is the C. Anyone know what the 2 is? Yeah. So it's this exponent that gets a bit ugly, but it's with the X. So which two transformations are always written with the X? The D and the K. Oh, so what's the 2 going to be? Yeah, the 2 is the K. And what's the 4 going to be? The D. So it's just in a different location. So we got A equals 2, K equals 2, D equals 4, C equals 1. Good question. That's a very good question. Does K equals 2 or 1 over 2? K equals 2, but we're going to talk about a horizontal stretch by a factor of 1 over 2. And so now what we're asked to do is list RST, right, in the correct order. So first of all, are there any reflections? Is K or A negative? No. So we don't have to list reflections. All right. So now we talk about stretches in any order. Vertical stretch by a factor of? No, you don't have to. The vertical stretch, you don't have to change. It's always the horizontal stuff that's weird, right? Remember, it's always this stuff that you're going to flip around. So a vertical stretch by factor of 2. There is a horizontal stretch by a factor of, what's it going to be, Sebastian? Beautiful. 1 over 2. Right? So for the horizontal stretch, that's when you do 1 over K. 1 over K. Okay. And then we've got 4 across and 1 up. For this one, let's just factor it and write AKDC. Okay, so if this is the equation, we must factor first. What are we factoring out? That's right, the negative. So we're factoring negative 1 out. You got time, Luke. Okay, so you're going to write AKDC. We'll do the last questions tomorrow. They're nice thinking questions. Okay. Well, let's write this down. A. What's A? What's K? What's D? And C? Great. Who's coming to extra help today? That's it? Just come and do your homework, folks. Get it done in half an hour and you're done.